Hello, everybody. It's about time to get started with the next set of research presentations on collective intelligence, technology, and algorithms. I'm Jason Burton. I'll be sharing this session. I think we all know the rules already. About 15 minutes allotted per presentation, with roughly 10 for the presentation itself, and hopefully about 5 minutes for questions. So without any ado, I'll just hand it over to Shiyan Zhang or Jeffrey Nickerson to present the first talk.
All right, can everyone see my slides here?
Looks good.
Great, awesome. So, hello everyone. My name is Shiyan, and my co-author Jeffrey Nickerson is also here. It is our pleasure to talk about our study about the coevolution of task and technology. So as we all know, computational technology is one of the driving forces of changes in work today. Technology changes the processes and skill requirements to complete tasks, and tasks shape the boundaries and identities of occupations. These characteristics of occupations in turn influence the design and usage of technology. So we really want to try to understand the relationships between these entities, and hopefully understanding those relationships can in turn help us provide insights on the evolution of the work ecosystem, which may help improve job design, education program development, technology design, and more. So unlike most studies that focus on work and technology, we didn't really use a labor economic lens here, nor did we focus on one specific occupation or technology. Instead, we drew inspirations from modular system theory to investigate the entire work ecosystem and the relationships between the key components. The concept here of modularity has appeared in different forms in theories, including ecological complexity and collective intelligence. The graph here is adapted from a paper by Tijuana that studies app architecture and their platforms, which is built on the theoretical foundations of Baldwin and Clark's work on modular design and Simon's notion of architectural near decomposability, which describes the independence among systems and the interdependence within systems. We see a parallel between the structural relationship of apps and their platforms and the relationships of occupation, task, and technology. Just like the apps can use the platforms as a resource, tasks can also take advantage of technology resource in the form of software packages. So here we see three key measurements that can represent the relationships among these entities. So the first one is the internal task distance, which we calculated by using the task and the average distance of that task with the rest of the other tasks within the same occupation. The second one is the task occupation distance, which is the distance between a task and the occupation it belongs to. And the last one is resource distance, which is the distance between a task and the technology resources that is used by the occupation the task belongs to. So what I mean by distance here is the semantic distance between the descriptions of these two entities, which we will go into further details later. So what we believe that these three measurements will have significant impact on the importance of a task. More specifically, what we conjecture here is the shorter the distance is, the higher task, the more important a task would potentially be. So with the first two, it's more intuitive to understand. So if a task is closer to the description of an occupation, that means the task is more closer or more similar to the core identity of that occupation. Task is more likely to be more important. And during our data exploration phase, we find that the first two distance are actually positive related. So the closer the task is to the occupation description, it's more likely to be closer to the rest of the task as well. For the last one, whether or not a task is similar to the technology used in the occupation will increase or decrease the task importance, we really don't know because we can really interpret it either way. So here we just hypothesize that the closer it is or the more similar it is to the technology available, the more important the task will be. So let's briefly look at the data we use. There are two major data sources. The first one is the ONET database, which is a database sponsored and released by the US Department of Labor. The first two tables are the examples for the occupation and the task data set. So each occupation will have a title and a description. And then each occupation will have a set of tasks. So here is one example of the task. It will have a statement that describes the task. It will also have a rating of the importance. And then what is not shown here is each occupation will also have a list of technology commodities that it uses. Unfortunately, ONET doesn't provide us with description of the technology commodities. So we use online sources like Wikipedia to manually fill in the blanks. So now we have the textual data on the descriptions of the occupation, the task, and the technology. We can transfer all of these textual data into high dimensional vectors by using text embedding techniques. So here we actually use the universal sentence encoder to embed all of these textual data. And then having the vectors, we can calculate the distance between each two of these entities. So after we have all of these distance calculated, we can test our hypotheses with regression models. We selected two sets of control variables, the embedding of the task descriptions themselves, and the embeddings of task description plus the 52 ability ratings, which is also in the ONET dataset. And then our main effect test would be the three key components of the distance measures plus the control variables. And as you can see, all three key distance measurements have negative effects on the skill important rating of a task, which support our hypotheses that shorter distances indicate higher skill important ratings. The reason we're interested in the task importance and its relationship to other structural properties of the work ecosystem, especially the usage of technology commodities, is that these are the characters that reflect the collective decisions and experiences of the job experts and worker groups. Task and technology usage also adjust to each other. More technology commodities are created around the more important tasks, and the tasks are designed with consideration of the technological tools available. Therefore, we really try to understand these relationships because they can provide signals to guide us through decisions when we design tasks and technologies. The results of the study show that tight coupling relationships enhance task importance. It is particularly interesting with respect to the relationship between task and technology, because many people believe that technology is replacing human labor, but what we are discovering here indicates that tasks that share greater similarity with technology are more likely to be considered important by the workers. So this suggests is that the how a task is done can be different, but the work itself is not disappearing, nor the human intelligence involved in this process. So given what we learned from the study, we believe this hierarchical view of occupations and tasks can provide understanding of the intertwined nature of the work ecosystem. Continuing using this modular system theory as a foundation, we have been experimenting with changing the level of analysis. So what you see here is we use task as the unit of analysis. We've done similar studies using occupation as the unit of analysis. We've also been incorporating network theories and techniques into the study because since we already have the distance measures, it makes it possible to build a network of occupations. Network theories here provide us with new ways of understanding the structural properties of the work ecosystem. Potentially, we can use random walk techniques to explore and predict connections between task and technology in the future, or we can build multi-level networks that represent the interactions between occupation, task, and technology, and use the dynamic network models to understand the systems and how they evolve over time. So because we have more and more job-related data is being collected every day, so there's really rich data out there. By adopting an ecology network perspective, we believe we can open up more theoretical and practical opportunities for future research, making the future of work a unique field, allowing very exciting interdisciplinary studies. Thank you.
Thank you for that presentation. Really interesting use of embeddings, I thought. I'll just briefly pause and wait for any questions to perhaps arise from the audience. And if nothing comes up immediately, I have a couple quick clarification questions. Okay, well, first we'll hear from Juan, if you're there.
Yeah. Yes. Can you, hi. Thank you for the interesting presentation. Sorry, I will try to set up my video as well. Can you measure somehow the effectiveness of technology supporting workers?
So right now, we're not actually measuring the technology itself. We're measuring the distance between the textual descriptions of the technology and what it does, and the task the workers are required to do in an occupation. So we're not measuring the effect directly, but more through the textual description of the two things and see how much they, how closely they're related to each other.
Thank you very much.
I have a quick question then, if I may. Just sort of, if you could clarify what is being captured when you say task importance. So you mentioned this was the workers' ratings from this survey?
Yes. Yes, so the task importance is a measurement from the ONET dataset, and ONET is a survey data collected throughout years, and every year they ask workers, experts, incumbents in different job occupations of what they do and how would they rate every task they do. So task importance is one of the ratings that they ask throughout this process.
Do we have any other questions from the audience? Okay, well, with just the remaining sort of 2 minutes of this block, I might ask one more question, which is, with this data, and this, I might be misunderstanding it, but can you speak to sort of some kind of causality? Like, does the task come before the technology or vice versa? Is that visible in this data?
I don't think it's that obvious if there is any causality. And also just speaking from like a common sense level, I don't think one necessarily comes before the other. I think it's kind of a circle in which we describe as, you know, they influence each other. In our presentation, we think how technology changes task, but in turn, task also change technology and how it adapts to different occupations and how it's being designed.
Thank you. I saw a hand, but it disappeared. If it comes back up, I think we can pick up the conversation in the LinkedIn group. So maybe with that, I'll just say thank you again to Shiyan and invite our next speaker. So if Daniel, Manuel, or Niccolo is here ready to present, I'll invite you to share.
Yep, it's me. Just give me a second. Okay, can you see my screen?
Yes, looks good.
Perfect. Okay, hi everyone, and thank you for being here. So let me introduce first myself. I'm a research scientist at the Max Planck Institute for Human Development in Berlin. And today I'm going to talk about some simulation work that I have been doing in the past year together with Dan Barkoczi and Manuel Cebrian on the indirect influence of bots on opinion dynamics. So we know that bots are common in most online spaces, from social media to online fora, and they are really like pieces of code that can behave like humans online. So, for example, they can tweet, like other accounts' content, following other accounts, and so on. So some bots, are totally benign, but others have been suggested to influence the public debate on a number of controversial topics, from polarizing human views to tampering with elections and so on. So our work started because we noticed two waves in the research on bots that offered very different conclusions. So these two waves are exemplified by these two papers here on the slide that were published just a couple of years apart from each other, both on PNAS. And the first wave was around the just after the 2016 presidential elections. And papers like the one that you see on the left offered a relatively bleak view of the situation. So this paper is by Stella and colleagues, and he mapped out the network of interactions between bots and human agents on Twitter. So the authors concluded that bots may influence information diffusion in social media systems, specifically by accentuating the exposure to negative, hatred-inspiring, and inflammatory content, thus exacerbating social conflicts online. And the second wave instead is kind of represented by papers like the one that you see on the right, and offers a more hopeful view, if you want. So this is work by Christopher Bail and colleagues who measured people attitudes also after the 2016 presidential elections, and noticed that actually attitudes of people who interacted with the Russian bots in this case had remained relatively unchanged. And in fact, they concluded that Russian trolls might have failed to sow discord because they mostly interacted with those who were already highly polarized. So nice contrast, but which one is it? And one thing that we noticed reading this body of research is that actually most of these studies only talk about direct interactions between human and bots. They don't include, well, first, the indirect influence that a bot might have via a recommender system. And second, the indirect influence that they might have via intermediary human agents. So what do I mean by that? A direct interaction is something that happens directly at the interface between two agents, one human or two humans, or one human and one bot. So for example, liking a tweet, reposting, leaving a comment, sending a follow request, etc. These are all direct interactions. And these sort of interactions are represented by the green arrows on this figure. However, focusing just on direct interaction neglects the fact that social interactions and influence happen in a highly mediated environment where content is curated by a whole system of algorithms that rank, sort, and present content based on certain predefined rules. And recommender systems, are a big topic, so I'm not pretending to give you any expert's perspective. However, we noticed that a bot capacity to influence humans via direct interactions is really limited by the number of people who directly engage with the bot. But as a bot, you have a much greater capacity to influence people if you influence the recommender system that curates people's content. For example, by skewing recommendations to be, I don't know, more extreme, to more extreme views. And this would have a much larger impact overall, because once you influence the recommendation system, now you are affecting effectively the whole network. So this is an example of a simple recommender system here on the right-hand side. So here I plot how likely an agent is to engage with content as a function of how extreme is that content. And the recommender system might learn an internal representation of what engagements to expect when it recommends moderate versus extreme content. And this is represented by the green regression line. But now one hypothesis that we made was that the mere presence of bots, represented here by the orange crosses, can really bias the model's learned representation by basically tilting this regression line that it learned from the green to the red one. And a second way that indirect influence can happen is also via intermediary human agents. And like before, once a bot influences one target human, it really effectively influences all the humans that that person will interact with. And so all our measures might be essentially an underestimate. And so what we did was we simulated 100 agents on a fully connected network on 1,000 different simulations. And each agent here is represented by a private or true opinion in the range between 0 and 1, and a public sort of expressed opinion that is a really noisy readout of the private opinion. So on each step, the agent is presented with a feed of other agents' public opinions. Think of it as tweets, and decides whether it wants to engage with it or not. But crucially, these public opinions or tweets, if you want, are sorted by our simple recommender system, which in our case, this was a logistic regression that predicts engagement based on the similarity between the content opinion and the agent's opinion. And the feed was then composed of tweets that were more likely, according to our logistic regression, to elicit engagement. And if the agent decides to engage with the content, then it is influenced by it. And the agent in our simulation updates their current opinion based on this content. And we use a Bayesian update rule, so to basically test the limit case of what would happen if we had all perfectly rational agents. And if the agent chooses instead not to engage with the content, then its opinion remains unchanged. So we also introduced one single bot in this network that basically was showing more extreme opinions than everyone else and didn't want to change their mind. We let the simulation run for 1,000 steps, and these are the very preliminary results. So on the left here, I plot the mean opinion shift in the population. And on the right, I plot the mean engagement with content. And you can see that just by introducing one single bot in the network, now the average opinion shifts towards the bot's opinion and engagement with content increases. But a more interesting piece of results is that if you look at how many agents directly engage with content that was produced by our bots, these are actually not many. This was about 2 to 5 agents on every simulation step. However, if you compare the average opinion difference between the same agent, so the same node in the network, in the 2 simulations, in sort of these 2 counterfactual worlds, so one with the bots and one without the bots, now virtually all agents of the network have shifted their opinion at least a little bit. So currently we are trying to disentangle, basically what better explains this variation that we observe that we observe whether it is the indirect influence of the bot via the recommender system or via other intermediary human agents. So in the meantime, stay tuned, and we will upload our preprint very soon. Thank you.
Thank you for that, Niccolo. Once again, I'll just pause and invite the audience to open with questions. Yes, Ralph.
Yeah, thank you very much, Niccolo, for super interesting work. I wonder, could it also work the other way around, that if you actually introduce extreme bots and if they actually don't gain traction, then kind of people with similar extreme views may also get down-weighted by the recommender system? Is that a likely scenario as well, so that actually adding extreme bots might actually decrease the influence of extreme opinions?
How would that work? Because now, like the recommender system would learn, basically, like the bot behavior would kind of pollute like what is the average human behavior, right? So if the bot is more extreme, the recommender system might be induced to think that actually the average human is quite extreme.
Yeah, but I mean, I guess that depends how the recommender system is kind of like programmed, of course. But I mean, if the bots actually don't gain traction, if they actually don't receive much likes, because of their extreme behavior, then other extremes might also, actually get down-weighted.
Yeah, this is a very good point. Actually, it's true. Like once, this is very, very speculative and theoretical, because of course we don't have access to the recommender system that are actually used on platforms which are way more complex than logistic regressions. But definitely, once you understand that mechanism, and now you can create really interventions using bots to actually reduce extremism or polarization. Exactly, yeah, by using like the mechanisms that you highlight.
Yeah, well, really, really cool work.
Yeah, thank you.
There are some questions in the chat. Niccolo, are you able to see them, or would you like me to read them aloud?
If you could read them, yes.
Okay. Well, Tom Grad has just directed you to a piece of literature if you're interested. And then Laura John says, thanks a lot for this very interesting presentation. How is engagement implemented in the simulation? Is it enough for a belief update to happen to only see the tweet, or must agents actively retweet or like to engage?
Yeah, this is great. Yeah, this was like a subject of lengthy conversations with the other co-authors. Yeah, what does constitute sort of engagement? And for us, it was in the end like the simplest choice was just to have like a binary engagement. So do I engage yes or no? And the engagement was simply basically taking the difference between the expressed opinion in the content, so for example in the tweet, and the sort of private opinion of the agent, and proportionally engage with that content. So the more distant the content, the more, like, let's say, inflammatory the content you can think of. Now the more likely I am to engage. And once I engage, yes, the update occurs in our simulation automatically. So basically, the agent updates the private opinion with the opinion expressed by that content.
We have one more question in the chat. So this one from Marissa Ponte. She asked, are these bots designed having cognitive dissonance theory in mind? So according to this theory, people invested in a given perspective shall, when confronted with contrary evidence, expend great effort to justify retaining the challenged perspective.
No, actually, yeah, this is an interesting point, but no, we didn't. Like we started from like the simplest bot that you bot an agent that you can imagine. So we basically built on top of various models in opinion dynamics that actually model agents as one, or agent's opinion as one number between 0 and 1, or -1 and 1. And they let neighbors sort of interact. So opinions change based on a neighbor opinion. So the sort of extra step that we added on top of this was that we split what is a private opinion. You can think of like, my actual opinion, even if I don't interact with the platform, and then an expressed opinion, which is basically what I tweet. And that split was done not really like to capture any dissonance or like theory of mind, but only so that the recommender system now could have only very sparse data points on a person's opinion, and he actually had to infer or learn about the true engagement function of the agent, even without observing their true opinion.
Okay, the 15 minutes is up, but Ralph, I think we'll have time for an extra question if you'd like to ask.
Yeah, so I was wondering, so in the beginning you sketched these two different, like, is it like good or is it a bad, the influence of bots? I wonder if that's the right phrasing. Isn't it more like, what is a good way to design your recommendation algorithm to actually, kind of reduce the influence of bots, right? Because they're, I think, isn't that more the question?
Yeah, I mean, as a scientist, I'm always cautious because our work is like always like very theoretical. But definitely, yes, like ultimately it would, the perfect scenario would be like a policymaker or like a private company designing an algorithm would take these results into account to actually not just maximizing engagement, but actually also trying to infer, like to weed out basically like bots influence.
Yeah, exactly. I guess bots can have a big influence or a small influence depending how you design the system, right? So it's not an either or system.
Yeah, instead of like amplifying a bot's influence, yeah, you want to sort of reduce it. Yeah.
Thank you.
Okay, thank you very much, Niccolo. That was really interesting. We'll continue on with the session, which is now my turn to present. So I will share my screen. Okay, I'll assume it's working and someone just holler if it's not. Yes, so I'm still Jason Burton, and in this talk, I'm going to share some preliminary results from experimental work that was supported by Nesta's Center for Collective Intelligence Design. And sort of the overarching objective of this work is to draw from the literature on the wisdom of crowds to develop machine tools to support collective deliberation and decision-making in online settings. So I'm sure many in this audience are already familiar, but in its most classical definition, the so-called wisdom of crowds refers to the phenomenon where the collective judgment of a group reached via averaging or other aggregation rule outperforms the individual judgments of the group members. And to understand why the wisdom of crowds exists, there are a number of longstanding analytical findings across the social and computational sciences. One of these is the diversity prediction theorem shown here, which provides a mathematical guarantee that the collective judgment will always be at least as good as and usually better than the average individuals in terms of error squared. And what it also does is formalize two ways in which the accuracy of collective judgments can be increased, either by increasing the competency of individuals or by increasing the diversity or the statistical independence of the individual's judgments. And this finding has important implications for communicating groups because it explains how communication and social influence can simultaneously be both good if it serves to increase the individual's accuracy and bad if it leads to too much of a reduction in diversity. And in more recent literature, it's been furthered by showing that whether the net effect of communication is ultimately good or bad for collective accuracy depends on the underlying network dynamics. So for instance, in its purest form, crowd wisdom requires each individual to have equal influence, as in this group of independent nodes. But once communication takes place, the collective judgment becomes a weighted average because some individuals are able to exert more influence than others. Yet in reality, there's yet another level of nuance here. because our social networks are dynamic and change over time. This can occur through both endogenous forces like homophily, as well as exogenous forces like algorithmic mediation online. And while this seems to have sort of alarming implications for society in the context of social media, where algorithmic mediation guided by factors like popularity could in principle be making us more susceptible to group biases, it also seems to suggest that that same type of algorithmic mediation could be redesigned for epistemic benefit so as to boost the accuracy of collective decisions. And so this is where our research question comes in. We ask, can collective accuracy be increased by algorithmically rewiring social network structure without knowledge of the ground truth? So basically what we're proposing here is a type of dynamic network where some algorithmic rewiring procedure manipulates who talks to whom over the course of deliberation with the aim of leading the group to collectively arrive at some unknown truth. So to explore this, we ran an online multiplayer experiment. We had 704 M-trickers and split them into a bunch of 16-person networks. And then we challenged each network to predict 10 near future events. And you can just see a couple examples up here that kind of ranged in topic. And for each event being predicted, participants would first act independently to make a probabilistic prediction and write a short rationale. And this was then followed by 4 stages of social exchange, where participants viewed the responses of their network neighbors and revised their predictions. And of course, most importantly for the experiment is each network was randomly assigned to one of 4 treatments, 3 of which involve rewiring algorithms that we sort of previously explored and developed with agent-based simulations. So the first treatment serves as a control or a baseline and simply puts participants in a randomly generated small world network for each prediction and holds the network structure constant throughout the social exchanges. So in this plot here, you can just see a simulated example of this where nodes are colored by their belief, or in the case of our experiment, their prediction, with bright red being 100% and bright blue being 0%. And then on the right side, you can just see how the distribution of beliefs or predictions changes over the course of communication. The next treatment is one of our 3 candidate algorithms, which we've called the mean extreme algorithm. Now, the aim of this algorithm is to boost individuals' accuracy by centralizing the network around potentially accurate individuals. So what it does is it first calculates the mean belief in a network and identifies whether it's closer to 0 or 1, so which alternative does it favor. It then identifies the agent holding the most extreme belief in favor of that alternative that's supported by the mean, and adds directed edges from that extreme agent to the 3 agents holding the beliefs furthest from it. Now, you don't need to get the nuts and bolts of it for the purpose of this talk. The main thing to understand is simply that this algorithm effectively steers social influence in a way to rein in outlying beliefs, which you can see in the distribution plots on the right, comparing the experimental treatment on the bottom to an otherwise matched static treatment on the top. The next one is what we call the polarized algorithm, and the aim of this one is to prevent a homogenization of beliefs and maintain a degree of diversity in the network. So what this one does is loop through the agents and identifies those holding the most extreme beliefs on either side of the spectrum, or in other words, the polar agents. And it then cuts all incoming ties to these agents so as to protect their beliefs from the influence of others. And then it will broadcast these extreme beliefs, so the beliefs of the polar agents, to the median agents in the network with directed ties. And once again, the sort of just main takeaway to see here is that this algorithm simply aims to lead a network's belief distribution to be more widely dispersed after communication. And finally, we have the scheduling algorithm. So this one differs a bit from the others in that it ignores the agent's beliefs altogether and instead prescribes or schedules a sequence of dyads for the participants to communicate information through. And the most important thing with this one to take away is that the algorithm is scheduling the dyads such that 2 people cannot meet if they have already met with each other, or if they have previously met with the same person. So in effect, this is preventing any redundant communication from taking place. So from the perspective of participants, the experiment is quite straightforward and looks like this, where you would first input your prediction independently, and then proceed through the stages of social exchange. And if you're in one of the experimental treatments, the network neighbors that you see on the right side are subject to change over the course of each prediction. And so once the groups complete the 10 predictions and the events resolve in the real world, we then calculate their average collective error squared and compare it across the treatments. So now onto our results. In both plots here, we show each group is depicted by a dot and split out by treatment along the x-axis. The bolded shapes with vertical error bars indicate the estimates and confidence intervals of a mixed effects model with random intercepts by group. And then the colored box plots in the sort of background indicate the raw spread of the data. So first, let's just focus on the plot on the left. Along the y-axis, we've plotted the average collective error squared and looked for a treatment effect of groups post-communication collective accuracy. And this one returns a statistically insignificant result. However, it doesn't account for potential confounders like the baseline competency and starting network structure in each group. So what we did on the plot on the right is sort of try to sidestep these potential confounders by looking at the effect of communication within each group. So instead, on the y-axis, we have the average change in collective error squared from the group's initial collective prediction to the group's final post-communication collective prediction. And here we do see a significant treatment effect that suggests when communication is mediated by the polarized algorithm, it will decrease collective error more often than not, whereas communication either tended to increase or had no effect on collective error in our other treatments. Now, of course, in these analyses, we've only assessed accuracy based on the observable binary outcomes, whether or not the predicted events occurred or not in the real world. An alternative measure of interest involves looking at how well calibrated these collective estimates are, particularly in the context of making multiple predictions. So that's what we did next. In short, calibration measures the extent to which subjective probabilities, so the predictions made by our groups, how well they match objective probabilities observed in the real world. So for example, of the events that you predicted to have a 70% chance of occurring, did 70% of those events actually occur? So in this plot here, we see that before any communication took place, our groups were all collectively well calibrated, with the slopes of the regression lines nearly aligning with the perfect diagonal. But once we look at their calibration after communication, we can see qualitatively a pretty interesting treatment effect. So in our control group shown in gray, communication led to overconfidence. The subjective probabilities were more extreme than the objective probabilities, leading to a more horizontal calibration line. And while the mean extreme algorithm seems to have exacerbated this overconfidence, the polarized and scheduling algorithms were able to maintain the group's calibration. The caveat, of course, with this analysis is that because our groups only predicted 10 events, these data are likely to be noisy because, for instance, there are only 2 events for which the mean extreme groups predicted 10%. So just to conclude, what can we take away from all this? Well, first of all, we recognize there are some important limitations to the study, such as a general lack of statistical power, and we aren't really advocating for any of the specific algorithms per se, including those experimented here. But we believe this experiment provides a proof of concept showing that algorithmic mediation with different rewiring algorithms can be used to steer the effects of communication and online social networks, making collective decisions. And so through planned future work, we're hoping that this line of research can be used to inform the design of new online deliberation tools and civic technologies. And just to end, I'd just like to say thank you to you all for listening, and thank you to my collaborators on this project. And if I can figure out how to stop sharing, I will. There it is. Okay. If there are any questions from the audience, yes. Okay, Ralph.
Thank you very much. Really, really interesting study. I was wondering, did you have a look at the Breyer score and how well individuals in different conditions performed in terms of the Breyer score?
Not explicitly. We sort of see there are some similarities with error squared and the Breyer score, being that, it's sort of a proper scoring rule, and that you wouldn't want to be overly extreme in the long run because you'd be average across them. Do you have some predictions about what we might be looking for?
Well, I mean, I guess, if you're trying to evaluate how accurate an individual probability estimate is, then using the Breyer score would, I think, be the appropriate way to do. Rather, the argument that you make is like binarizing is hiding some of that information. So that might be worth to check because indeed, like what you said, the calibration might be tricky. But on an individual level, you can just measure each individual's accuracy based on directly on the Breyer score. So it's a more richer way, I think, of quantifying accuracy.
Yeah, that's a good point. I mean, to be honest, with these analyses, I'm sort of skeptical. I don't really like how we're sort of averaging averages, and we're losing a lot of information in that. And so there's plenty more analyses we hope to do with this data set, and hopefully we'll find some interesting stuff and could look at Breyer scoring as well.
Yeah, thank you.
Yes, Louis.
Yeah, really interesting presentation. It makes me wonder if you've thought about using personality of the participants as a rewiring factor, so that the strong-willed people maybe are matched up with other strong-willed people rather than overpowering the introverts or something like that.
Yeah, this is a really interesting point. Well, we haven't considered it, is the short answer. But yeah, I can see your point. At the moment, the algorithms are just taking as input the numeric estimates, right? And even in our sort of conceptualization of why this should work, it would actually be better to take into account the sort of text rationales, right? Because we want to sort of highlight diversity. So two people could have the same prediction of, say, 60% for completely different reasons, but our algorithm would miss that. And so kind of like looking at things like personality or these more sort of, I don't know, social aspects, there's a lot of different inputs that these algorithms could take. And I think obviously you have to design them with the input in mind. But yeah, in short, really good idea. We haven't looked at it, but yeah. Yes, Ben?
It seems like there might be some interesting analysis related to the presentation from earlier today about how much people adjusted their estimates based on what they received from their neighbors, and using that as a measure of implied confidence and seeing how those things interact.
Yeah, no, definitely. That's an excellent point. And even in, for instance, just adding to this, when we were developing the algorithms, which are fairly arbitrary ultimately, like we tested them with agent-based modeling and saw like, okay, these ones should work. Let's try them out. But we're just using a DeGroot sort of model of opinion dynamics. And in that you have this, this self-weight parameter, right? And so you could, in principle, design an algorithm that identifies people who have these higher self-weights and therefore are more resistant to social influence, which may be indicative of them being confident and more accurate. But yeah, it's a great point.
Yeah, you could use your same data set to test that same prediction from earlier about, are the people who adjust their weights less actually more accurate?
Yeah, that's a good point. Yes, Jeff?
Yeah, Jason, when I was looking at the questions, I was wondering if there's any interesting information in the questions versus the strategy. So for example, it occurred to me that picking the future price of Bitcoin is, say, very different than estimating the number of jelly beans or something. And so is there a dynamic related to the questions, perhaps?
So we have some follow-up work that at the moment is just simulations, but our answer is yes, absolutely. Maybe not so much in the substantive topic of the question per se, but rather the belief distribution that each question elicits, right? So, I mean, if you have predicting positive numbers like jelly beans in a jar, people typically display a highly right skewed with a fat tail, right? And the algorithm that works best for that context will be different than, say, a context that elicits a normal distribution around 50%. So it's sort of exactly what you're saying, but maybe in a different framing, if that makes sense.
Makes sense.
Okay, I think I went a bit over time, but I'd like to invite our final speaker of the session, which is Louis. If you're ready to go, please do share your screen.
All right, I am sharing my screen. Okay. So today I'm going to be talking about swarms and hyperswarms. And this is work I've done at Unanimous AI by myself, Louis Rosenberg, Colin, Domnauer, and Gregg Willcox. And just as a quick outline of what I will be talking about, first I'll talk about swarm intelligence, and which is nature's way of amplifying the intelligence of groups. Then I will talk about artificial swarm intelligence, which is how we connect human groups into real-time swarms over computer networks. And then I'll talk about just a couple of academic studies that show how ASI amplifies the collective intelligence of network groups successfully, but I'll also talk about the strengths and weaknesses where ASI outperforms traditional wisdom of crowds, statistical aggregation, when we have diverse groups, but ASI equals wisdom of crowds when you have lopsided groups with a large majority, even if that large majority has low confidence. And so the research goal is to enable confident minorities to better overcome unsure majorities. And that's what led us to hyperswarms, which is a new architecture for ASI that better empowers confident minorities. And so really quickly, swarm intelligence is nature's way of optimizing the intelligence of groups. What nature does not do is nature doesn't take votes, take polls, conduct surveys. There's no survey monkey in nature. What nature does is it form, and nature, there's no big data sets in nature, no big data or machine learning. What nature does is it forms systems. So real-time systems with feedback loops that enables groups to converge on optimal solutions in real time. Biologists call this swarm intelligence. And really the important thing about these natural systems is they are real-time systems. And ultimately it's why birds flock and fish school and bees swarm, is because they can converge on smarter decisions together. And so the big motivating factor that drives our research group is, if birds and bees and fish can get better in these real-time swarms, can people do it? And it turns out that we can. And this is a natural swarm. Over the last 6-7 years, my team at Unanimous AI have been studying natural swarms and developing algorithms and interfaces that allow humans to form similar swarms online. And so this is an artificial swarm making a forecast. What you're seeing is about 100 people connected from anywhere in the world, and they're all working together in real time. And each of the little magnets that you see is controlled by a person with their mouse or their touchscreen to modulate the magnitude and direction of their opinion in real time. And then there are algorithms that are watching all of their behaviors to determine how the swarm should move. And so a swarm is a real-time system with participants acting and reacting and interacting, revealing the strength of their convictions to the underlying algorithms. And a key thing is that swarming evokes deep behavioral data. We're not asking people to just give us an opinion and tell us to estimate their level of conviction. We're just asking people to behave. And so the algorithms see this cloud of behavior, and what we get by having people behave and as they interact in real time is this more authentic representation of their confidence and conviction. And then the algorithms have been trained to identify what those behaviors mean and control the direction of the swarm itself. The last thing to know about traditional swarms is that they are systems with feedback, meaning a question appears on everybody's screen and they immediately behave. The AI algorithms watch the behaviors, control how the swarm should move, and then people change their behavior because the swarm is moving in a direction. So the people behave, it impacts the algorithms impact the people, and they converge together on these very good solutions. And so we've been studying swarms, like I said, for 7 years, we've partnered with many universities and done formal studies that show that swarms are pretty successful. I'll just mention two. We published a study with research at MIT last year where we looked at forecasting financial markets, a group of people forecasting the price of gold, price of oil, S&P 500 every week for 20 weeks. They did it alone. They did it as a majority vote statistical aggregation, or they did it as a real-time swarm, and the swarm amplified their accuracy by 26%. So big improvement when they work together as a system. We published a study last year with Stanford Medical School looking at radiologists. Chest x-rays would pop up on their screens. They would then have to forecast the probability that these patients had pneumonia. They did this alone. They did this as basically majority vote, or they did this as swarms. And what we found was we reduced their diagnostic errors by over 30%. And we see this in study after study that these real-time systems offer real value. And so it brings me to the strengths and limitations, which is that swarming, we see outperforms typical wisdom of crowd when the populations are split among a plurality of opinions, when you have this diversity of opinions. And we see that small pluralities of high confidence very, very often can overcome larger pluralities of low confidence, which is really where the strength of these systems happen. But swarming basically reduces to wisdom of crowd. It equals wisdom of crowd when you have this large majority that can overpower the minority. And that's true even if the majority has low conviction. It can still overpower a confident minority, which led us to this goal of enabling high confidence minorities to better overcome these unsure majorities. And that's where hyperswarms come in. And so to understand a hyperswarm, it's worth making one comment about a traditional swarm, which is that in the swarms that we typically work with, each participant interacts with all other participants in real time. It's basically a single dynamic system with a flat structure. With hyperswarms, we're now looking at a new structure where each participant interacts with a random subset of the full population, maybe 20% of the full population. In addition, each of these random subsets overlaps with n other subsets. And so what you see in this figure here is the architecture of a hyperswarm, which has 20 people in the population. Each of those people is in a random subset of 7 other people. They're only exposed to and interact with 7 other people, but their subset overlaps 7 other subsets. So each person is basically in its own unique swarm that overlaps other swarms. And so we end up with basically a swarm of swarms, where everybody influences everybody else. Nobody's exposed to the full population at any moment in time, which means that the interactions are local in these subgroups, but can propagate across the full population very, very quickly. And the key here is that by combinatorial chance, some of these local distributions will be pretty different than the global distribution. I might think that I'm in the majority because I see a local group where I am in the majority, but really the global, I might be a part of a large minority. And so because of this, some of these local swarms, confident minorities will be able to sway unsure majorities if they have higher confidence. And over time, that minority opinion can propagate across the population. And so, so basically the hypothesis is that this hyperswarm structure will enable some portion of the confident minorities to survive as a local majority and expand its sentiment across the population. And in fact, in some cases, it will enable these local minorities to actually become the global majority. And so we ran a comprehensive simulation study so we could really understand the dynamics before we do this with real people, which we are now doing. And so we created a simulated decision where people would either believe that the answer is A or B. We had a simulated population with a distribution of views of either A or B of varying confidence levels, a simulated hyperswarm of a global population P and a subgroup size S. And then we had simple behavioral rules that govern switching based on, do I think I'm in the majority or the minority, and what's my confidence, will I switch? And so in particular, the swarm, the simulation worked like this. Here's a simulated hyperswarm structure of a population 20, subgroup size 7, and each subgroup overlaps 7 other subgroups. Here's a population distribution where 60% of the population believed A, that's the blue line, that's the majority. 40% of the population believed B, that's the orange line, that's the minority. And the important thing is that the confidence of the minority people, on average, B, is higher than the confidence of A. So that was the populations that we simulated. And then we had these simple behavioral rules. If I find myself in a local majority, I'm not going to switch because I'm basically seeing a population that reinforces my belief. If I find myself in a local minority, I might switch. I might switch with a probability of 1 minus my confidence. If my confidence is 100%, then I know the right answer, then I'm a 0 chance I'm going to switch. If my confidence is 50%, and I find myself in a local minority, in this case, 50% chance that I might switch my opinion. And then if a participant has already switched, I've already switched once from my original opinion, but then I find myself in the minority again because other people switched around me, then the probability that I switch back was just my original confidence. So these simple rules, and then we ran the simulation. Each trial would just pick a random seed from the population distribution. Each test would run 5,000 trials. And then we ran many tests where we looked at a variety of majority distributions from a very small imbalance, 51% majority, to a large imbalance of 65% of the population believes this one majority opinion. We varied confidence differentials so we can see how confidence impacts the hyperswarm, and we varied subgroup size from just 10% of the population to 40% of the population. And so in a particular trial might look like this. We pick a random seed. The green is the minority, the red is the majority. And in this case, 60% of the population believes the majority opinion. And then as it propagates with these rules through the simulation, what you see in this trial is that some of these minority seeds are able to expand over time, and basically by the end of the simulation, and it is really just about 10 seconds of interactions, we end up with the majority overcoming the minority. In this case, we end up with 60% majority. The minority opinion gets to 60% of the population. So it flipped. The minority flipped the majority. And so that's one trial. We then would run that configuration across 5,000 trials. And what we ended up seeing was that when we start with a 40% minority with these starting conditions, we saw that the minority became the majority 56% of the time. So more than half of the time, it was able to flip the majority. When we ran the same exact tests on a flat swarm, not a hyperstructure, 0% flipped. So this was encouraging by itself, but then we looked at trying to understand the parameters that affect it. So we looked at, how does the minority fraction from a minority that's just has 35% of the population up to a majority that was very close, 40 to 60. And when you get up to 45, 55 minority, then almost all the groups flip. And so that's very interesting. We also looked at what happens when you vary the confidence differential between the populations. And as you might guess, when the confidence differential gets bigger, again, with a big enough confidence differential, again, you get almost all of the groups flip. And then we looked at subgroup size, and we looked at from 10% of the population up to 40% of the population being these subgroups that overlap. And as you can see, it's kind of optimizes around 20%. Once you get to about 25% of the population, it falls off quickly. And that gives us some initial guidelines for the human tests that we've been running. And so in conclusions, what this simulation study told us was that hyperswarms have potential to enable confident minorities to sway less confident majorities in real time. Subgroup size of 10 to 25% of the full population worked well in the simulation, but then degrades quickly. And we saw hyperswarms up to a 65% majority, so a pretty large majority able to to be flipped by a confident minority. And that even gets even bigger when the confidence differential is bigger. And then the next step is human trials. And we've, over the last 6 months, been doing human tests, initial human tests with hyperswarms. And we're seeing behaviors that match the simulation pretty nicely. And we are seeing that hyperswarms are being effective to empower confident minorities. So with that, happy to take questions.
Thank you a lot. That was super interesting. I'll just invite the audience to ask any questions. I'm conscious that I have led us over time, but that's completely my fault. Yes, Natalia.
Yes, hi. Fascinating talk. I was thinking about your example of radiology, the paper you published on X-rays. And one of the thoughts that occurred to me is that the actual value of this financial value may not be very high because radiologists are very, very expensive. And to have any sort of big collective look at the same X-ray financially probably is not worth it as compared to doing a CT scan. However, as I was doing this critical thinking, it occurred to me that there is a huge value in what you're proposing in a different area of, especially when it comes to minority opinion, and that has to do with the creation of ground truth in training system for AI radiology. And I'm wondering if you thought about it, because basically when you are currently, the ground truth in various high professional tasks is aggregation of expert opinions. And it's often the case that the minority has the right opinion and has some confidence around it, but that gets overshadowed by just aggregation. Any thoughts on that? It just sounds like a great application of this.
Yeah, no, great questions, and all your points are exactly right on. So the work we did with Stanford Medical School for radiologists, it's worth mentioning that those were small swarms. Those were 5 or 6 radiologists in a swarm. That said, your point is still well taken. 5 or 6 radiologists is still expensive, and so we actually did a follow-up effort with Stanford Medical School where we looked at a triage system where first they used their machine learning to because one of the really interesting things was they compared the same exact X-rays with machine learning, just straight machine, no humans, versus the humans, and what we found was that they had different strengths. The small human groups were really good at the edge cases, the unlikely cases, whereas the machine learning was really good at the cases that it had seen in its millions of trials. And so we created a triage system which would say, okay, on the vast majority of cases, machine learning is fine, but on those cases where the machine learning does not have high confidence, you can then give that to a swarm of 4 or 5 radiologists. And when you go through that process, we were able to get accuracy up to over 90% accuracy because by combining the 2 strengths. And so it's a great point about just the expense.
Sorry, I'm thinking a little bit in a different way, because what we're talking about in general at this conference about sort of when when it's particularly useful. And in some of these cases in professional knowledge, like radiology, the answer is not known. There is epistemic uncertainty.
Right. So your ground truth point is also really a really good point.
So my only point is that you would see great value in listening to a confident opinion of minority when there isn't a certainty and standard in the field. And there, for example, at Stanford, there are, like they do bone age, I don't know if you're involved in that, there are 6 panelists, only one of them may be right, but the ones with justification should be heard, and that would be a great application. So I'm just hoping you do that research with them.
Oh yeah, no, and the ground truth is a great application, and we actually we've been working with some different medical schools. UC San Francisco has been looking at ground truth for orthoscopic X-rays, but it's a great application, a ground truth. Because
I hope you do it. It will help us all. Please.
Yes, Tom.
Can you hear me now?
Yes.
So a very interesting presentation. I have one question. You showed a very interesting way with hyperswarms that the confident minorities could persuade the unconfident majorities. The question is, do you have any thoughts about when that's a good thing and when it's not? It seems quite possible that in some cases, confident minorities would be wrong. And so you wouldn't want to set up a situation where they had too much influence. Have you thought about that? Do you have an answer or guideline?
Yeah, so we think about that all the time because we that's true even when we run just traditional swarms, which is we want participants that are, we would say, well calibrated, like who are good groups of participants. And what we find is the best groups of participants are people who know what they know and know what they don't know. And that's why it actually works so well. Like we were worried when we would work with people with as high expertise as radiologists, because they're already so skilled. Can we even make them better? But it turns out they're good because they know when to be confident and they know when not to be confident. And so that's really, in some sense, the definition of expertise. We also run with just average people, forecasting sporting events, and we find that even with average people, they're pretty well calibrated. They know when to be confident, they know when not to be confident. And but when it's really important, sometimes we run a screener survey, and before they even come into the swarm, so we could weed out people who don't know what they don't know. For example, if it's a group of sports fans and we say, who do you think is going to win these games? And then we ask them at the end, what percentage of these games do you think you're going to get right? If they say 90%, we know that they don't know nobody can predict 90% of a set of games. So they don't even know enough to know how hard it is. And so a simple screener survey can be used to get a calibrated group of people. And once you have a calibrated group of people, we see it actually works very, very well.
Great.
Jeff, is your hand still raised or is that a new hand?
No, I don't have a question, thanks.
Okay, great. So that will conclude this research presentation session. We went a bit into the break, but we have a little 3-minute rest until the next panel. So thank you all for listening.